In their quest to understand the first stars and galaxies that lit up the cosmos, astronomers are still in the dark but getting closer to enlightenment, one discovery at a time. That's the incredible, inescapable conclusion from unprecedented discoveries by the James Webb Space Telescope, or JWST, the $10 billion time machine that just officially closed its first year of observations. Designed to glimpse the faint infrared glow of the universe's earliest luminous objects, Webb's vision reached back into the first few 100 million years after the Big Bang, allowing it to obtain more and better data about newborn galaxies than any other facility yet built. But its haul of galactic baby pictures has proved more bountiful than most researchers dared to dream. Simply put, candidate galaxies in the early universe are popping up in numbers that defy predictions, with dozens found so far, and that makes scientists freak out. As Charlotte Mason, an astrophysicist at the University of Copenhagen, said, "We really weren't expecting this." In the weeks and months following JWST's findings of surprisingly mature early galaxies, theorists and observers scrambled to explain them. Could the bevy of anomalous big and bright early galaxies be illusory, perhaps because of flaws in the analysis of the telescope's initial observations? If genuine, could they somehow be explained by standard cosmological models? Or just maybe, were they the first hints that the universe is more strange and complex than even our boldest theories had ever supposed? And the Big Bang Theory, was it wrong? Join us today as we dig deep into how the James Webb Space Telescope broke the universe. Let's get to the point. To understand the dilemma, let's go back to when the universe was believed to have been formed. After the Big Bang, the infant universe began cooling off. Within a few million years, the roaring plasma that filled space settled down, and electrons, protons, and neutrons combined into atoms, mostly neutral hydrogen. Things were quiet and dark for a period of uncertain duration, known as the Cosmic Dark Ages. Then something happened. Most of the material that flew apart after the Big Bang is made of something we can't see called dark matter. It has exerted a powerful influence over the cosmos, especially at first. In the standard picture, cold dark matter, a term that means invisible or slow-moving particles, was flung about the cosmos indiscriminately. In some areas, its distribution was denser, and in these regions, it began collapsing into clumps. Visible matter, meaning atoms, clustered around the clumps of dark matter. As the atoms cooled off as well, they eventually condensed, and the first stars were born. These new sources of radiation recharged the neutral hydrogen that filled the universe during the so-called epoch of reionization. Through gravity, larger and more complex structures grew, building a vast cosmic web of galaxies. Meanwhile, everything kept flying apart. The universe is expanding rapidly. The astronomer Edwin Hubble figured out in the 1920s that the universe is expanding, and in the late 1990s, his namesake, the Hubble Space Telescope, found evidence that the expansion is accelerating. Think of the universe as a loaf of raisin bread. It starts as a mixture of flour and water, yeast, and raisins. When you combine these ingredients, the yeast begins respiring, and the loaf begins to rise. The raisins within it, standing for galaxies, stretch further apart from one another as the loaf expands. The Hubble telescope saw that the loaf is rising even faster. The raisins are flying apart at a rate that defies their gravitational attraction. This acceleration appears to be driven by the repulsive energy of space itself, so-called dark energy, which is represented by the Greek letter lambda, pronounced y lambda. Plug values for cold dark matter, regular matter, and radiation into the equations of Albert Einstein's general theory of relativity, and you get a model of how the universe evolves. This lambda cold dark matter, or LCDM, model matches almost all observations of the cosmos. One way to test this picture is by looking at very distant galaxies, equivalent to looking back in time to the first few 100 million years after the tremendous clap that started it all. The cosmos was simpler then, its evolution easier to compare against predictions. Astronomers first tried to see the earliest structures of the universe using the Hubble telescope. In 1995, over 10 days, Hubble captured 342 exposures of an empty-looking patch of space in the Big Dipper. Astronomers were astonished by the abundance hiding in the inky dark. Hubble could see thousands of galaxies at different distances and stages of development, stretching back to much earlier times than anyone predicted. Hubble would go on to find some exceedingly distant galaxies. In 2016, astronomers found its most distant one, called GNZ11, a faint smudge that they dated to about 400 million years after the Big Bang. This was surprisingly early for a galaxy, but it did not cast doubt on the LCDM model, in part because the galaxy is tiny, with just 1% of the Milky Way's mass, and in part because it stood alone. Astronomers needed a more powerful telescope to see whether GNZ11 was an oddball or part of a larger population of puzzling early galaxies, which could help determine whether we are missing a crucial piece of the LCDM recipe. That's why the James Webb Space Telescope, or JWST, was born. Renowned as the largest, most powerful observatory ever launched from Earth, the JWST was built to revolutionize our understanding of the universe. Stationed 1.5 million kilometers away from earthly interference and chilled close to absolute zero by its tennis court-sized sunshade, the telescope carries a giant segmented mirror and exquisitely sensitive instruments that were designed to uncover details of cosmic dawn never before observed. And that promise was kept, as the first discoveries were obtained within just weeks after JWST's full operations. They were beyond astronomers' wildest dreams. It has seen galaxies breathtakingly close to the dawn of time, probed the atmospheres of exoplanets in unprecedented detail, and provided stunning new views of worlds in our solar system. But it's just getting started, as Webb's vision reaches back into the first few 100 million years after the Big Bang, allowing it to obtain more and better data about newborn galaxies than any other facility yet built. At stake is nothing less than our very understanding of how the orderly universe we know emerged from primordial chaos. Webb's early revelations could rewrite the opening chapters of cosmic history, which concern not only epochs and faraway galaxies, but also our own existence here in the familiar Milky Way. As JWST scientist Mark McCaffrian, a senior advisor for space and exploration at the European Space Agency, said, "You build these machines not to confirm the paradigm but to break it. You just don't know how they will break." Researchers use a version of the Doppler effect to gauge the distances of objects. This is similar to figuring out the location of an ambulance based on its siren. The siren sounds higher in pitch as it approaches and then lower as it recedes. The farther away a galaxy is, the faster it moves away from us, and so its light stretches to longer wavelengths and appears redder. The magnitude of this redshift is expressed as EZ, where a given value of Z tells you how long an object's light must have traveled to reach us. One of the first papers on JWST data came from Naidu, the MIT astronomer, and his colleagues, whose search algorithm flagged a galaxy that seemed inexplicably bright and unaccountably distant. Naidu dubbed it Glass Z13, indicating its apparent distance at a redshift of 13, further away than anything seen before. The galaxy's redshift was later revised down to 12.4, and it was renamed Glass Z12. Other astronomers working on various sets of JWST observations were reporting redshift values from 11 to 20, including one galaxy called CRS 1749, or CR2Z71, whose light appears to have left 13.7 billion years ago, just 220 million years after the Big Bang, barely an eye blink after the beginning of cosmic time itself. These putative detections suggested that the neat story known as LCDM might be incomplete. Somehow, galaxies grew huge right away in the early universe. "You don't expect to see massive galaxies," said Chris Lovell, an astrophysicist at the University of Portsmouth in England. Indeed, in a study published in November, researchers analyzed computer simulations of universes governed by the LCDM model and found that JWST's early bright galaxies were an order of magnitude heavier than the ones that formed concurrently in the simulations. Some astronomers and media outlets claimed that JWST was breaking cosmology, but not everyone was convinced. One problem is that LCDM predictions aren't always clear-cut. While dark matter and dark energy are simple, visible matter has complex interactions and behaviors, and nobody knows exactly what went down in the first years after the Big Bang. Those frenetic early times must be approximated in computer simulations. The other problem is that it's hard to tell exactly how far away galaxies actually are. In the months since the first papers, the ages of some of the alleged high redshift galaxies have been reconsidered. Some were demoted to later stages of cosmic evolution because of the updated telescope calibrations. Suurs 1749, for example, is found in a region of the sky containing a cluster of galaxies whose light was emitted 12.4 billion years ago, and Naidu says it's possible the galaxy is actually part of this cluster, a nearer interloper that might be filled with dust that makes it appear more redshifted than it actually is. According to Naidu, Suurs 1749 is weird no matter how far away it is. It would be a new type of galaxy that we did not know about earlier. If early JWST observations are robust, how could these mysterious galaxies be explained? One is that early galaxies might be surprisingly efficient at forming stars, converting nearly all their gas into stars instead of just a fraction of it. This could explain how early galaxies grew so massive so quickly, but it seems unlikely to account for the abundance JWST observed. Another possibility is that we misunderstood the universe's evolution at the epoch of reionization, and it was more transparent than thought. This would allow JWST to see further than expected, but nobody knows how this could happen. The third possibility is that dark matter could be made of warm particles instead of cold ones, moving more quickly and unable to coalesce into galaxies as readily as dark matter currently is. A fourth is a more exotic possibility, where the universe began not just with a Big Bang but with a brief inflationary burst that stretched space-time, as predicted by some versions of string theory. Then, at the very beginning, quantum processes would have created dense regions that quickly turned into galaxies. Ultimately, the solution may not involve overturning the LCDM model, but instead improving it. This happened before when new observations prompted astronomers to refine their models. For now, the discovery of early massive galaxies remains an exciting puzzle that motivates scientists to keep probing the mysteries of the universe. To conclude, JWST is not breaking cosmology, but shedding new light on the early universe, revealing complexities that challenge our understanding. As more data is collected and analyzed, we may find that these early massive galaxies can be reconciled with existing theories, or they may lead to new insights that refine our models.